Since we're aiming to make hash collisions infeasible, let's analyze how likely collisions are for different sizes of hash codes. Suppose we have a hash table where our array has 256 elements and we have some ideal hash function h. That is, for all the keys you can give it, it's going to equally map them across the different array slots, 0 to 255. If we randomly pick values, each of which is distributed over this case, how many items do you have to hit until you expect a collision? That is, at what point does the probability of a collision go above 50%? Intuitively, you might think, well, when you filled the array halfway, so something like 128, but that's not right. If you work through the probability, it turns out the probability that two items don't collide, it's easiest to think about don't collide and watch until we get down below 50%. If you just do 2, then it looks sort of like what you would expect, 99.6. And if 3 that don't collide is 98.8, and 4 that don't collide, it looks like this is going down slowly, and you will have to go halfway or so before you get down below 50%. But notice that the difference between 99.6 and 99.8, which is 0.8, is smaller than the difference from 98.8 to 97.6. That's 1.2. And that means the difference in probability is accelerating. And if we work out all the numbers, we see that after 8, we've already dropped down below 90%. And after 16, it turns out we've already dropped down below 60%. And the answer that we were looking for was 20. After you've hashed 20 items, only 20 items, then you're more likely than not to somewhere along the way have encountered a collision. And 20 is much less than half of the size of your table. This non-intuitive effect of the probabilities is well known, and it's sometimes described as the birthday paradox. If you have a room with 23 people, and their birthdays are randomly spread across the year, it turns out, even with only 23 people, you're as likely as not to find 2 people who have the same birthday. And when you go up from 23, you're more than having your probability again, so by 30 people, it's extremely unlikely that everyone has different birthdays. More generally, we can characterize this in terms of the size of the array as a power of 2. So if we have 2 to the n different slots in our array, and again, if you're thinking of a hash table, n can't get very big. It can't be more than 64, certainly. Or, something on the order of 40 is already way too big for a hash table. Still, we can ask the question in these abstract terms. Here is the formula for that, expressed in terms of factorials. And factorials are notoriously hard to simplify, but it turns out a pretty good approximation of this formula is 2 to the n divided by 2. That's the point where the probability of a hash collision reaches 50%. So our idea about halving things was on the right track, but it's a half in the exponential, not in the absolute number 2 to the n. In other words, the probability of a collision grows with the square root of the size of your table. The good news about a square root is it keeps going up as long as we keep increasing the size of n, and the bad news is it goes slower and slower as we go. Just to double check, if we take 256 that we were using, that is n equals 8, and this formula suggests that k would have to be 16, which is not exactly 20, but it's in the right neighborhood. For a hash table, n can't be more than 30 or 40 or so. But for our cryptographic hash, we're not actually making a whole table. We're not making an array that has all possible messages in it. We just want to get the number, and the number is all we want. So we can use a much larger n than you would for a hash table. If we use 128 bits for our hash code, this is on the same scale as our chunks in a block cipher, then we expect to need 4 times 10 to the 9th different messages before we would find a collision. That's a fair number, but it's not intractably many. 256, though, starts to be 10 to the 38th power, and a 512-bit hash code is going to be 2 to the 56 or 10 to the 77th. That is a very large number. Is it large enough for our purposes? Well, a good thing to remember as a programmer is that 2 to the 256 is on sort of the same scale as the number of atoms in the universe. So, if we use a hash code of 512 bits, that means you would have to pick every atom in the universe and look at its hash code before you are likely to find a second atom that matches the hash code of one that you saw before. So that's an awful lot of messages. All we have to do is make sure that our hash function is one where only this brute force attack of looking at every atom in the universe is the one that would let you find collisions.